So welcome back to the afternoon session. In the morning session, we learned that the zeros of L functions and the prime numbers have a kind of duality. Okay? That was, so people tried to study the distribution of prime numbers, and they ended up in studying the zeros of L functions. Okay? So I mean, around 1797, Legendre observed that the primes up to x, say 1, 2, x, this grows like x by log x. Well, it isn't exactly like x by log x. He wrote something like x log x plus some linear function. And later he estimated that a should be 1. And for B, it got some particular value. So this is the primes, the number of primes up to x is almost of the size x by log x. This observation which we now call the prime number theorem, originated from Legendre, and well, Legendre around 1797, but Gauss, yeah, actually Legendre had a book on angular theory, and in this book he made this conjecture, whereas Gauss recollected that around 1793 he also came up with a similar observation. So we are going to see in a few days how people who are proving their observation. We will actually take the shortest route to the proof of the prime number theorem, that is to Newman's proof. But before we go into that, we will study some basic properties of primes, as well as we will introduce some tools which will lead us to the proof of this. So this theorem, as Ritu was shared in the morning session, this theorem, this observation was proved by Hadamard and Delahaye in 1896. Right. This was by Hadamard and and they proceeded in a way. Riemann actually chalked out a way of proceeding. In 1859, he wrote a paper. Riemann's main work is it actually chalks out a path to prove the prime number theorem using zeros of the Riemann zeta function. So this was 1896, and Riemann's thing was, Riemann's paper came out in 1859. But even before that, Chebyshev obtained a quite nice result. He proved that. So this was around 1858. So there exist two constants A and B, between which pi x will be bounded. And this was Chemisch's result, and it was rather elementary in comparison with the prime number theorem. Okay? So the nice thing that Chemisch observed is that instead of counting the primes up to x, which is actually seemingly rather difficult task, we saw that if we instead try to estimate this, the product of primes which are less than or equal to x, this seems to be easier task than counting the primes up to x. Well, here we are, we'll see soon that why this is also sort of counting. Okay? Counting with some weights for each of the primes. But for the moment, note that what Chemisch did is that he studied this product and saw that this could be, one could easily give an upper bound for this. Okay. So this was the observation that product of theorem, the first theorem that we proved in this lecture, and this is going to be a rather simple thing. So consider the product of all the primes p which are less than or equal to n. Then we are going to show that they are bounded above by 4 power n. Now note that at first, before going into the proof, if we prove this, then what does it mean? Take the log on both sides. So it will say that if you take the log of the primes and primes less than or equal to n and add them up, that sum is bounded above by n times some constant, log 4. So this is basically like you are, instead of doing like summation 1 p less than or equal to x, that is what the prime number theorem does, right? This is just pi x. It counts the primes, just you are summing 1 for each of the primes. Now, if you take a log here, then instead of summing over 1, what you are doing, you are doing the sum over log p less than or equal to x. So if this claim holds, then we know that this sum is of the size, okay, so this sum is actually less than log 4 times. Okay. So this is just an equivalent statement of this, but I am just trying to see, show you that instead of this sum, we are taking an weighted sum. So let's now do this proof. This proof is rather simple and elementary. So check first that for n equal to 1 and 2, this is trivial, right? For n equal to 1, we have, yes? There is question? Okay, so ask them to move to the YouTube stream. This one is streamed by profile. Yes. You can also provide the stream link. It's provided in the. So n equal to 1. For n equal to 1 and 2, you have the first one is time to effect. That's of course less than 4 power 1. And then the next one is 2 times 3, that's 6. And here you have 4 squared. So for 1 and 2, it's 3. And if you keep on checking, you'll see that this is what you do. Now we are not going to do that because this is what we are going to do is prove by induction. So we prove by induction. That is, we are not going to check for every integer, but we check for n and we go for this one. Okay, note one thing first, that it suffices to show this for larger than 1. So for all n larger than 1. Alright? So in particular, that means, okay, you can check for one more n that is equal to 3. That means you take the product here, 2 times 3 times 5, and that is 30. And on the right hand side you get 4 cubed, that is 64. Of course it works, right? So it is true for n equal to 1, 2, and 3. Now, suppose it is true for some n larger than or equal to here. So up to what n we check? We check for n equal to 1. Right? And for n larger than 1, we saw that this is true. Okay, so you can keep on continuing to check it. So you can actually check it at say 5. Some n from where you can start the induction. And then you start it. For n greater than 1, this means this is the first value that you will take here is 2. This is then n less than 5, and this check the for n less than 5 this is still true. Now so let's assume that the modes for n and the modes for all primes less than or equal to n plus 1, and we just add to them for all primes less than or equal to n plus 1. That means you have the product of the primes p less than or equal to n plus 1. This is less than or equal to less than 4 power n plus 1. Now note one thing, that the product of primes which are between n plus 1 and 2n, so primes which are strictly between n plus 1, well, it is strictly greater than n plus 1 and less than equal to 2n, but less than equal to 2n doesn't make it. Alright, it's in a non-prime thing, so you can also have this here because we are not in the case where n is equal to 1. We have already taken by hand for that. And this one is, well, this number actually, that this divides 2n plus 1 factorial by n plus 1 power. Well, n factorial times n plus 1. Okay, because none of the prime images here, none of these primes divide this one, okay? But all of them divide numerically. And this is just the binary coefficient when you choose n. Okay? So this is an integer which you can write as this ratio of factorials, and all these primes divide the numerator but not the numerator. So this product divides this, right? And this one is just a coefficient in the expansion of 1 plus h to the power 2n. So put x equal to 1 and get this inequality, that this is less than equal to 2 power 2n, right? Which is equal to 4 power n. Okay? So that means now if you plug these two, that is up to n plus 1, this product is less than 4 power n plus 1. And between n plus 1 to 2n, it is, well, this divides, this means that this is less than equal to this, right? So this divides you can replace by less than equal to. And then this 2 2, if you take the product of these two things, you get that if you, well, actually, here we are confident we are plus 1. So, and the thing was to show it up to 2n plus 1, right? So here we can check for 2n plus 1. Okay. Yes. And then this is 2n plus 1. Below we have again n factorial. So this is instead of, otherwise this so p less than, here we are going from n plus 1 to n plus 1, and here it is 2n plus 1 factorial divided by n factorial by n plus 1 factorial, and now this is right, this one is perfect, and then we have okay, fine. So this is 2 power 2n plus 1, and wait a minute. So this is 2 times 4 power n, and upstairs we have 4 power n plus 1. So if you multiply these two together, what do we get? We are getting the product of all the primes p less than equal to 2n plus 1, and that is less than 4 power n plus 1 times this one, 2 times 4n. Okay. So somewhere we are getting an extra factor of 2. How can we remove it? Should we remove it, right? Let's see again. Yeah. So up to n plus 1, we are assuming that it is the claim holds, and then we are proceeding. Okay, if we start instead of n, what happens? Yes. This is not fine. It's good.
If we take n equals to 2, then it doesn't hold.
For n equals to
2.
For n equals to 2? 2 minus 1. Perfect. Yes, I see. Yeah. Because we are not going up, but we should go one down. Thanks a lot. Okay. So this is 12 minus 1. Okay. So then from n plus 1, if we are going up to n square minus 1, what I want to say is that it's not very nice to work with the minus 1 here. Instead of, why don't we work with plus 2 here and plus 1 here? Because we know that plus 2 cannot be a prime, so this will go to plus 1. Okay. And then let's figure out how to get over this. Okay. So we are again considering the primes from n plus 1, we should go up to 12. Now there is no problem in going up to n plus 1, right? We are in the same situation, and what we are trying to show that this one, so to show that the product of the primes p less than or equal to n is less than or equal to, so I mean, by the assumption, by if you show that, then this is 2n plus 1, and this is less than, strictly less than 4 for 2n plus 2, right? So showing this suffixes for showing this one. And this one we want to break it into two parts. One part should come from this observation that these primes are dividing numerator of some binomial coefficient but not the denominator, whereas the other part will come from the induction hypothesis. So let's revisit the proof. Okay? And instead of trying to correct it, let's read it once. Okay, so this part of primes, we write it as the product over the primes which are less than or equal to n plus 1 times the primes which are between n plus 1 and, well, not 1 plus 2, but we are considering this one. So this is the primes, all the primes between n plus 1 and n plus 1, right? Okay. But the primes between n plus 1 and 2n plus 1 are actually also all the primes between n plus 1 and 2n plus 2 also. Right? So that means that will lead us to the proof of this one, for the even ones. Okay, let's proceed and check. Because we know that if we prove it for the odd index, we are done. But for the even index, it doesn't necessarily imply that we get it for the odd index. So for the first one, it is less than equal to, sorry, strictly less than 4 power n plus 1. This is my induction. For the second one, we just saw that this part is less than equal to 2 power 2n plus 1. Yeah, it was less than 2 power 2n plus 1, right? And this extra plus 1 was making all the problem. Right. So otherwise, we should go up to yes. Okay. And then 2 plus 2. Yes, we will get 2 plus 2 here, and then what will be for it? So I would remember where are we going
So
on?
the boundary is not the binomial coefficient.
Yes.
The boundary is not the binomial coefficient.
Right.
The coefficient is 2 times in the exponent.
Anyway.
The coefficient is 2 times in the exponent.
Oh, right. And there that will be a plus. Very good. So, did you get the logic? That is plus 1 plus 1 over 4 2 plus 1. Right. Now, in this, how does it go? This 2 plus 1 is 0 plus 2n plus 1 is n plus 2n plus 1 n plus 1 plus plus n choose. And these two things are the same. So they are operating twice. Right? And so that takes care of this extra plus 1 that was happening. So this one is then bounded by 2 power 2n plus 1, and since it is operating twice, I mean this thing is operating twice and this is divisible by this part, that means less, I mean half, sorry, twice of this is less than equal to this one. Right? So let's write it down here clearly, and then we will just put the estimate here. So n plus 1 less than t less than 2n plus 1, and the product is over all the primes. This divides 2n plus 1 choose n plus 1, which is equal to 2n plus 1 choose n, both occurring in the expansion of 2 power 2n plus 1. So each of them is less than this divided by 2, that is 2 power 2n. Alright, so we just put it here, and that takes care of this extra plus 1, right? So you have this, and this is equal to 4 power n plus 1. Okay? And that completes the induction, the induction step, because this product is just equal to this one. Okay? That the product of all the primes up to 2n plus 1. So finally we have got that product of all the primes up to 2n plus 1 is less than 4 power 2n plus 1 for all n larger than 1. And that proves this thing. Now, as we saw that this just means that if you take log on both sides, the sum of the log of the primes up to some, I mean log n is just a number, some x. So you're summing all the logs of all the primes up to x, and that is bounded above by 4 times log of that number. I mean here it was log n, and then it was log n also. So that log n could be replaced by some other number, some random number x. So it will come out to be this one. Yes? Yes. Why should we, don't we assume? Well, this induction argument actually goes from n to 2n plus 1, right? And yeah, I mean what the question what it was asked for 2n, I mean, if it is true for 2n plus 1, then it is true for 2n plus 3. Indeed, we are actually proving this. But nevertheless, instead of assuming it all the way up to 2n plus 1, we are just going halfway up to that. Note that it's a strong induction hypothesis. That is, you are not assuming that it is true for 2n plus 1, you are assuming it is true for all the numbers less than or equal to 2n plus 1. That in particular includes n, right? So, if you assume that it is true up to n, then we are showing that it is true for 2n plus 1. Okay. We are assuming up to n plus 1 and going up to 2n plus 1. But nevertheless, I mean, the jump is from n plus 1 to 2n plus 1, but if you go to 2n plus 1, I mean, if you jump by 2, that actually includes this, right? I mean, what I want to say is that the question is, if we go properly the way we do induction, we go one step at a time, right? So indeed, it's a valid question, that is from 2n plus 1, we should go to 2n plus 3. Now, suppose we are trying to prove it for 2n plus 3. And where are we beginning? We are beginning for 2n plus 1, the induction hypothesis was to assume it for n plus 1. Right. So for 2n plus 3, we should assume it for n plus.
We are assuming for n plus 1 and we want to prove it for n plus 1.
So from n plus 1, we went to 2n plus 1. Now if we go in this manner, we should work with n plus 2 and go for 2n plus 3, right? this one into
So assuming for 10 plus 1 we also
yeah, and what I'm saying is that if we, so it's not like we are assuming for 12 plus 1, we are assuming for all integers less than equal to 12 plus 1. This is called strong induction, right? And this is also a valid way of doing induction, right? So if we assume it for all the integers less than equal to 12 plus 1, that includes in particular n plus 1. Or if you in particular want to go up to 12 plus 3, that would include n plus 2. Right? And since n plus 2 is inside this set of all integers less than equal to n plus 1, indeed we are assuming it for all integers up to n plus less than equal to n plus 1, and in particular we are using this one to go up to 12 plus 3. So I hope it answers the question. So now, where were we? We wanted to now take the logs on both sides. And that is the thing that differential did. So we counted the primes with the weight of the logs, the weight has the logs and not just one. So Shakespeare defined functions which we come up again and again till we go up to the proof of random theory. Shakespeare's first function. What is that? Directs. You are summing over all the times. You are taking log p and p is equal to x. So this is basically just like taking the log of this product. And then you have x second function, that is xyz, which is sum over all the primes present, well, not primes, but now you are summing over the prime powers. So e power k present with x log p. Now let's see that the prime number theorem is equivalent to showing that since the first function or second function grows like x. Now what do you mean by grows like x? Okay, let's at first make this or grows almost like or grows like, make this more precise. So what do you mean exactly by this? So prime number theorem, let's state it first. We are of course not going to prove it today, but just to introduce the notation. What does it say? Phi x, that is the number of primes of x, is of the size x by log x. What does it exactly mean by of the size? That just means that if you divide this by that, it is, wait, this is the notation. If x is of the size gx, that means that limit fx by gx. If you take the, well, fx is of the size gx, and here of course what is assumed is that x is going to be infinity. So this limit as x goes to infinity is equal to 1. So we'll show that the prime number theorem, which is stated here, is equivalent to this. before we do anything more, note that psi x was a sum over many more things than theta, right? Theta x was just summing over primes, and this is summing over prime powers. So there's apparently a paradox which would not be so, because it will, if they are of the same size, that would just mean that the contributions from higher powers are negligible with respect to the contribution from first power. So let's look at the situation and think more clearly. Know that, for example, consider this situation, that is p squared less than equal to x. What does it mean? It just means that p is less than equal to x power half. Right? Instead, if you consider p cube less than equal to x, that will imply that p is less than equal to x power 1/3. Right? So, such primes, that is, such primes whose square is less than equal to x, or cube is less than equal to x, or kth power is less than equal to x, those will be counted in theta root x, or theta cube root x, or theta x power 1k, 1k. So in other words, psi x is not only theta x, that is, you are not only summing over the primes which are less than equal to x, but you are also summing over theta of x half, because you are considering p squares which are less than equal to x, and the power x, therefore 1/3 primes whose cubes are less than equal to x, and so on. So on up to which power of x? When the power was less than the allowable x, right? So x power what? 1 by yes, but what is k? So you can write out k here, but what is k? Then k is equal to, and what it means, after theta x power 1 by k, anything else will be just 0. So this will give the least contribution. That means 2 would be less than equal to this, right? If even the prime 2 is not less than x power 1 by k, because x is some, we are assuming that x is some positive integer, or something on the real line. Now x power 1 by k, where does it go if k goes to infinity? It goes to 1, right? So at some point this gets smaller than 2, right? And then the output from this, theta of that, is equal to 0, because it's not even counting the prime 2. Okay? So you have to go up to the case where 2 is, where 2 is still less than x power 1 by k, because when the impact is reversed, your function theta outputs nothing, it's just 0. So that means 2 power k is less than x, that means k is less than, well, not exactly less than equal, because if it is equal to, it still is counted, right? So k less than equal to log 2 log x raised to 2. So that will just imply that psi x is bounded by log x raised to 2 and so on. Note that theta x half is less than theta x, because here we are summing log p's for all the primes p which are less than equal to x, and for p's we are counting summing all the log p's for the primes which are less than equal to root x. So you are considering much less primes. The number of primes you are considering is apparently much less here. I can say that apparently much less here, because this just connects with some condition that we saw in the first half, that which said that there exists a prime between x square and x plus 1 square is still open, right? Okay. But nevertheless, at least you can say that the set of primes which are less than or equal to root x is containing this set, right? So even if we cannot say that there is a strict inequality between the number of primes here and there, we can say that at least this is less than or equal to this, right? And for the higher ones, of course, now we can say that there is a strict inequality, but we can just work with a less than equal. So this one on xi x is less than equal to this times theta x. Now, what happens there? So theta x, what is theta x? This p less than equal to x log p, right? And we have seen that the product of the primes up to some x is less than equal. So we saw the product of the primes p less than equal to x. This is like this, right? So now, if you take logs on both sides, well, we didn't quite see this, but we saw it for integers. Okay. But from there, getting this is not very difficult. So try it, yeah? And if you are stuck, we can discuss it. So product of primes p less than equal to x less than 4x, and then this we have, suppose we have this, then take the log on both sides, and we have summation over log p less than equal to x, that is just theta x. This is less than x times or log 4 times x. So if you now plug it there, what happens? This is equal to log x coming 2 times log 4 times x. So you are getting that it is, well, this is some constant times log x log x. Okay. But we can make it even precise. We can show that this is actually less than some constant times x, and actually that would follow from Schuster's theorem. This is and of course we have theta x is bounded above by cycles. Okay. So can I immediately make it a bit better? See? How? Yeah, let's check. Okay, there is some, yeah, of course there is some cancellation. Log x and log 2 here, and here is log 2, this up, the 2 limits here, and this is 2x log x. But it's still not such a good bound. We would like to have just x there and not log x. Alright, think about it, how to make that precise, more precise. Okay, what time is it? Yeah. It's about 3. So we can take a short break before we go into the tutorial session. This way. is intertwined with the leaf convolution. So first, let's introduce what is convolution of functions. But even before that, let's define what are additive functions. What are those? Just some function from the set of natural numbers to the set of functions. So just some sequence. Sequence of complex numbers. Now please pay attention because soon we are going to solve exercises, easy exercises, these are just fast on this. So then additive functions are those of form f of m in n for all m in n. This is a covariant split. Maybe I just write this instead of just brackets. So additive functions. And then there are quantitative functions. For all a and a, such that this is true, and it's the same condition here as well. Now these are called additive or multiplicative functions, and if you do not require this condition of this e of m and n to be equal to 1, then you call them if this is so if these two equations hold for all m and n, for all m and n without this condition we have, not necessarily having this condition. That is, for these ones we have this, and also for the ones we do not satisfy this, we still have f of mn plus f of n plus n plus f of n. We call it completely additive. These are called f is completely additive. And if for all in n we have f of mn as f of n times f of n, we say that f is completely multiplicative. So your first exercise, give me examples of such functions. Yes. How much tax is 18%? Otherwise, is there any charging for it? And is it being used for this one? Huh? Oh, we compare with yes, sir. Or otherwise, if it runs straight out, you can ask the participants to join in the stream. Okay. So, yeah. This was the active function, this was a multiplicative function. Okay, so we were just looking for examples of such functions. At first, perhaps getting examples of completely additive and completely multiplicative would be easier. Yes, David?
If x equals to x squared can be completely multiplicative.
if x equal to x square is an example of a complete geometry. Meaning here. Yes, of course, an example is x square or in or okay. So this is completely mathematical. How the other three cases?
So e to the power x completely identical.
Perfect. Wait a minute. E power x. E power mn is not e power n plus power n. Log. Right. Yeah. Log x. And the other examples like completely additive and multiplicative.
Quotient function.
Yes.
Quotient function.
Euler quotient function. Yes. Which one?
Additive but not complicated. Sorry, multiplicative but not complicated.
Multiplicative and complicative. Right. So Euler quotient function phi n is multiplicative. But not completely multiplicative as we just mentioned, because there will be up to that
4, 6, 5, 4, 6. 4 into 6.
4 into 6, okay. So phi of 4 is 2 and phi of 6 is 2 also, right? And phi of 24 is what? That is that you are counting the numbers which are less than 24 and is
4. 4 is 2, 8.
so this is your example. That's but you could have taken 5, 2, 5, 4. So you don't have to compute what is exactly function of 24, but you could have just counted how many things are less than the number that you are considering and do the co-practice. Okay. And that leaves you with only one example of a complete additive function. I think that is not too obvious, but if you could give me an example of that.
Additive but complicated.
No, yeah, right.
Log of phi.
Log of? Okay. Let's take. Sorry. That is correct. Log of phi into sector. So let's say, and first it should be additive, right? And since phi of m is equal to phi of m and phi of n, you get that log of phi m is equal to log of phi m plus log of phi. That, and then it is not completely additive because phi m is not completely multiplicative. So we just saw the example of all these kind of functions, and now I would like to introduce two more functions. One is this one, Mobius function, which is very helpful in convolutions. So can I write this further? some prime. If n is not divisible by square root of some prime, that means it's just a product of, say, r unit primes or k primes, right? So for those square root numbers, mu n is defined as minus 1 to the power k if n is a set of primes, a product of some ei1, ei2, etc. That it is, it's a product of k primes. So of course this and the first thing could be clubbed together because here the set of lines dividing n is just the integral. So there is 0 primes. And then you get getting just minus 1 plus 0. So can you tell me which kind of function mu n is? Multiplicative, additive, complex multiplicative, complicated, which kind? It's multiplicative. And why not complete multiplicative?
If there is a common factor, then x
Yes.
is not squared.
If you multiply, then on one side you get a square root prime, which makes the set. That side is it. Whereas other side you have minus 1 power something and minus 1. So it is a multiplicative function. And now we are going to define a function which is neither of any of this form, and this is what is a very important numerical function which we will occur again and again. Well, of course, mu n will occur, and also this one, lambda n, called von Neumann function. So this is defined as log p if n is or of some prime p and 0 other place. So for every n which is a power of prime, this function is log p, otherwise it is 0. Okay. Any questions? So we have already seen this function just a while ago. Where?
So we should second function.
Very good. Yes. You show me. Same tips.
Second function.
There we define it with ix as the sum of log p plus x for k is greater than x. Right? What we are doing? We are actually summing the one-man function over all the things which are less than x. So this is nothing but the sum of lambda n, sum of lambda n less than x. So such things, that is, where you are going from one function, summing over it on over the integers which are less than equal to x, or we will also sum over divisors. So whenever you are given some basic function and you are summing over it to get another function, we call this one the summatory function of this one. And what we mean by summatory function, it will vary from case to case. Sometimes it will be less than equal to such things. Mostly it will be such things. But till the time when we are in a domain of data convolution, this sum and sometimes this sum will be instead not in less than equal to x, but summing over the divisors. It will also. So once we define the convolution of the functions, define it immediately actually. Suppose f and g are commutative functions. Then the convolution of f and g, or integral convolution, this is defined as the sum over all the divisors p having n if p times g of n by g. Okay. So here we are taking some integer n, and the linear convolution is defined in this way. You can see that this is assumed with the number theory function or arithmetic functions. There we wrote number theory function. Here we are writing number theory function, and there we wrote arithmetic functions. They mean the same thing. So here, now we note a few things about the convolution. First thing is that it's commutative. Of course, you can replace d by n by d. So this will give you this. Now the next thing is that is there any identity element of convolution? That is, what I want to say is that is that function some identity function. So some function with which you take the convolution of f and you get f back. What function it should be?
One, where n equal to 1 and 0 otherwise.
Right? Because we just want to get f of n out, right? So here, when this is n, this will be just 1. Right? For everything else, it will be 0. So define this function, say, let's call it the unique function. Where should I define? Over here. So here, define let u n be defined as 1, n is equal to 1, 0, otherwise. Then note that if star u is just f, right? Follows from the definition. So this function which we defined in this one here, actually this you can also write as un is just a box of 1 by n. You see? Because for n equal to 1 it is giving you 1. For everything else it is just 0. So this is the identity function of linear convolution. So it got commutativity, and associativity is actually trivial. I mean, if so this is commutativity. Associativity if star G star H. Yeah, it is actually trivial because here you are, what do you mean? You are taking, you are doing the convolution over, it's like d divided n h star G of, well, this is different, maybe you should try this. Try to show that this is associative and it's not a very trivial. So Please say. And of course, we could write it in this manner, but we can write it also in some other manner, and then we rather easy to. And next, we have to break this one, right? Go on. But if you simplify the notation a bit, then this is kind of obvious. We don't have to manipulate the brackets. You're done? Wait for others. So only to proceed. You just wrote it down in this manner and then wrote D like this and proceeded, or you do something else. You have your Chandra. Sure. Sorry. Alright. So yeah, that actually makes life much easier to write this in as a product of more than one or two factors. So it's actually you are doing the same thing, but just in a different way. So we define it in this manner, right? F of D times G of N by D, where D is divided N. Right? We could have written this also as summation over D times D dash equal to N F of D and G of D. Okay. So we are writing the same thing here and there, but I mean just the notation is different. So if we do like this here, then this one, this of GIAN of course, instead of writing it in this manner, we can write it as product over three things. Well, at first product over two things like this D and D dash and D2 maybe. Okay. D1 for this one, D2 for this one. Their product is equal to n. Okay. Now you write it, this f star g of D1 as just a product of some factor of D1 times some other factor of D1 whose product is equal to D1. And the product of them all is equal to n. So this would be just the sum over f of d g of d dash and h of d double h. So at first you plug it like product of d dash and d dash and then break it. Basically you are also doing the same, but this gives off the associativity immediately. So this can be written as h star a of n. That's just one line. I'll do the computation. It's very nice. Okay, now immediate application of the associativity. So wait. We still got associativity and identity. We have even yet proved the inverse, right? What we are trying to do, we are trying to show that this function, this convolution is giving group law over some set of identity functions. So we'll go into that very soon. But first, consider this one. Actually, instead of denoting it u, since it's an identity, we can denote it by I. That would be easier. This is the identity function of every function, right? So, because we will call something else the unit function. The unit function will take one and all the inputs. Define the unit function. Okay. Un, which is equal to 1 for all n. And let's first compute the convolution of mu with u. So consider the sum over, we'll just compute this. Mu star u of n. What's that? U is identically 1 for all n. We call it the unit function. The unit function, well, for identity function, let's use the notation I because it's easier to it's easier to identify if we use I because I for identity. And we just saw that if we use this function, box of 1 by n, then this is actually giving this. For any function, if you take the convolution of this with identity from left to right because it's commutative, you get f back. Now the question is that if you are considering this function instead, u, and if you are taking the convolution of mu with u, what are you getting? The identity function. Okay, let's check. The summation mu d and, well, mu d times u of n by d, which is equal to 1. So we don't even need to write d by d n. Okay. And then why is the identity function? Also, what you declare for this to be an identity function? That it is taking the value 0 for all n's larger than 1. Otherwise, at 1 it's obvious, right? Because mu d is just mu of 1, which is equal to 1. So this claim is of course true. It's trivial. 1 if n is equal to 1. So all you require is to show that this sum mu d, d dividing n, this is mu 0. So this is 1. can write mu t as the product of the mu distributed over the prime powers, that is dividing d. And of course, if d is divisible by some square, then it's 0. So all we have to care about the primes, which is, as long as d is square free, we have to work with that. So then mu d times n, what will it become? Product of sum over, say, p1, p2, pk divides n, union p1, p2, right? Then the sum is over only the co-prime divisors. So, square root divisors of n. Okay? That is the prime product of primes which are dividing. So now this one is just the sum over p1 pk divides n minus 1, so we got p. Okay? But that's not what you said, right? You said that divide this instead. Divide n. Right.
Yes.
Of course, yes. So we write n as p1 power p1 pk power at, and then mu n is equal to mu p1 mu pk at, right? And so you can do the same thing with d, right? So so instead of writing this here, you want to write this sum mu d as one plus mu p1. If sorry, if n is of this form, you just want to write this sum mu d as just mu p1 plus mu p1 or p1 times 1 plus mu p2 plus mu p2 power a2 1 plus mu pk mu pk power ak. There's a thing about it. And then you just have to look at here because the rest are all zeros. Right? That was the idea. Or that was nothing. So what was the idea? Yes.
Then you can do the summation equal to n divides p1 p2 plus pr, because it does not depend on the square factor.
Yes.
You can just take the distinct prime
Yes.
or the distinct prime.
Right.
p1 to another pr. You can do that. G divide p1 to another pr
Yes.
mu of d.
Okay.
Then we can that time we can think about how many prime.
All possible product of primes from all possible square root numbers we are dividing in, right? And there will be 2 power k exceptions, right? You can take any of the primes dividing that, or you cannot choose any. So then if you don't choose any, then that gives you 1, and for everything else you are getting those many primes. So you have 2 power k choices, and then for each of these k choices, it's just minus 1 to the power of the number of primes. Okay?
You can use 1 minus 1 to the some plus binomial is
1 minus
1 minus 1 to the power 3.
1 minus 1 to the power k. Right? Always. Yeah. Sure. That's a very nice idea. Also, you can direct. So, is this here what we wrote there? It's basically the same thing, because you see all the higher powers vanish, and then you have 1 minus 1 here, 1 minus 1 here, 1 minus 1 here. So it is basically 1 to be 0. I mean, well, what we are saying is that mu power pk is equal to 0 for not only mu power pk, sum over this for k running from 0 to any n, any arbitrary n. Right? And then since mu is multiplicative, sum over the divisors of n would just be products of such things. And each of the factor is turning out to be 0. So if we multiply, find it to be 0, so we get 0. Alright. So indeed this is giving you that mu d is equal to 0 and sum over mu d is equal to 0. That means that here we are having that the sum is equal to 0 if I'm honest. Okay. So yes, as you identified, mu star u, this is indeed giving you the identity function. Alright. Now time for a very short exercise, a nice exercise. Summation Fn times mu of Fd times mu n by d, n by n. And it's a very short exercise because we have everything that we require for this. This is the chart sheet. It's gone. But you wrote a paper to go to the stream.
Actually, you can write that capital F of n equals to function d divided f of d into u of n by d.
If as in capital F as
In the first line,
the first line is
there is only f of d. That means f of d into 1, and we can write 1 as u of n by d.
1 as u of n by d, right?
So it becomes f star u.
Right?
So if we take u on the other side, then it gives f star mu.
Okay, we can actually, but you can also convolute this with mu, right? You don't need to, I mean, it's the same actually. On the other side, then you want to invert it.
Yes.
And that means just convoluting with mu, right? Because mu is the inverse of that. So indeed, that's the idea. So since A is equal to f star mu, and now that implies that f star mu is giving me f star u star mu. Okay? And you know that associative is there, that's why I have not wiped out this line. So that means you can do this I which is mu if. Okay. So now another exercise. Is show that lambda n, the whole member function, is equal to sum over mu b log of a by d by d. Once we're done, it's like
we just write in as the product of prime factors.
yes.
You can in the same way in discrete factorization, the summation that has
Right. So you're trying to show that lambda is mu star log. So then what we should show? I mean, what suffices to show?
you can do the d-device that you want to that way.
Yes, yes. Okay.
Same way you can do that.
Actually, the same way.
Exactly. So tell me, you should take the in convolution with what? The inverse of mu. And what is that? U. Okay. So this is equivalent to show that lambda star Q is equal to log. That is log of n is equal to lambda star n. Right? So that implies you have to show that log n is equal to summation lambda d divided n. Right? Now, what does it mean? Summation lambda d divided n. That is, we are summing over the prime divisors of n, because not prime divisors, the prime power which are dividing n. Right? So that means for each prime dp less than equal to n, we are taking the sum over sum of log p as many times the power is divided this. So that means if n is equal to p1 power a1 or pr power pr, say, then log n. Well, at first, just look at this. What is log n? Log n is summation ai log pi. I n for 1 to r. Isn't this the same expression? Because here you are counting the primes. You are summing over log p as many times as the power pk divided by this. So you are actually counting p once this for p1, p power 1, p power 2, etc. up to p power k. That is, you are counting for all these powers. So this is basically exactly the same expression, summation log p less than equal to n, that is all the primes less than equal to n, such that k, well, and the sum is running for over all the primes, that is obvious because it is running k is dividing n. The k is the highest power. Well, not exactly the highest power. Actually, this is running from over each power of the prime p and p prime. Okay. And of course, we learned that k is greater than equal to 1. Okay. Because otherwise, we will have log p contributions from the other primes and the primes which is not dividing this. So this is basically the thing that we wanted, right? So this is just sum over d dividing n lambda n. Okay. And d dividing n lambda n means that this is summation d dividing n lambda star u n. So log is lambda star u, and therefore lambda is equal to mu star log. That's this. Right. Thanks a lot. Yeah, here is also. Thank you. So now the next thing. Now the next exercise is even funner. And is this function, right? The Euler Russian function. And you know that think of this phi is equal to product over, well, n times product over 1 minus 1 by t divided by. Now start with that description that phi of n is the number of coprime integers. Sorry. Coprime to n and less than or well, it cannot be equal to, of course, unless n is equal to 1. So less than n equal to 1 actually claims this for n equal to 1 little descriptive here. So equal to n. Okay. And suppose we don't know this. We have only this description of phi. That is, we are counting all the numbers which are less than equal to n and coprime to n. Show that. this is this one. We took that as an example, but we have proved this. Yes.
So starting summation of k equal to 1 to n. Summation k equal to 1 to n.
Okay.
N. British integer of 1 by GCD of n comma k.
1 by. Oh, again.
British integer of
Okay.
1 by
1 by.
GCD of n comma k.
Right.
Then take this sum.
So y of n is this. I was kind of explain why this is true.
Because it is the number of integers which is less than n or co-prime to n. For co-prime, we get GCD of n comma k equal to 1.
Right.
So this integer will give the value 1, British integer value 1. Otherwise, it will give 0. So we count the sum.
Yeah. So unless the GCD of this and this is equal to 1, we are getting 0. Yeah, otherwise we are getting 1. Perfect. Yes. And then
Then we break the sum, summation k equal to 1 to n. And we know that summation of d divides in mu b equal to this function.
then this is just the ID function, right?
Yes.
So this is here. We are toward n I of GCD of n comma k. Right? Then you want to write I as mu star u. Right?
Yes. Interesting.
Mu star u of GCD of n comma k. Right? And then
Then this summation.
u we don't need to consider, we just have to take mu because this is ideal one. Alright, so this is summation k run to 1 to n mu of GCD n comma. Wait a minute. Then there are some. Very sorry. Is there a summation here? Summation b divides GCD of. Okay, let's just write n comma k. Important notion for this. So this is right?
Now d divides GCD of n comma k means d divides n and d divides k.
Perfect, yes. So this is summation k running from 1 to n, summation k divides n, d divides k, of n, right?
Now the sum runs over k equal to 1 to n and k divides k. So we write k equal to some d into some e.
Right, okay, so we write k equal to d times some e. Okay.
Now if we fix the divisor d divides n,
Yes.
so the sum will be summation d divides n and the
Summation, okay, so you want to switch the sum.
yes.
Okay. Yes. So we have k equal to e times e. So e is k by e. So we switch this one. From here, that is phi n is equal to summation over d dividing n, and what is the side? So this goes out, d divides n, k goes in, and then k is this d times some number e, which is, well, which is, wait a minute, e is k by d, right? And how big can e grow? It can grow up to k by d. Right? So d divides n and e less than equal to k by d. And what have inside is
mu of
E of t, which is constant for all of this. So we can take it first. Now if we divide it in mu d 1 which is equal to by mu. Right? And then we are basically inviting this. So we have here summation d divided n mu d times n by d. And then you can take the n out. Okay? So we have n times summation d divided n mu d by d. Then
now we can break this sum as a product of the primes because this function is multiplicative and
yeah, both mu and d they are multiplicative functions. Right?
so there this sum over the universe
This is completely multiplicative, but since mu d divided by d is multiplicative.
so this function also multiplicative product
Yes.
function. So we want to check only on the prime powers.
Sure.
And for higher prime powers, this function is 0.
Yes.
So this becomes a product of t, 1 plus mu p by t, and mu
Right.
p is minus 1.
Minus 1. Perfect. Yes. So this, so spreading, so since this is a multiplicative function, what we are using here is that summatory function of multiplicative functions is multiplicative. And that's an easy exercise to check. So here we are using the fact. We also used it earlier when we broke this sum over mu d as the sum over the product over the sum of the prime powers. So here we are still using that summatory functions of multiplicative functions is multiplicative. And that is giving you here n times the product over, since it's a multiplicative function, the sum, so we can just take the product of the times in 1 plus mu p by t, because the higher powers vanish, and then mu p is just minus 1, so we get 1 minus. Perfect. Thank you. So this is all for today. We will meet again at 11 a.m.